There's a kind of silence so deep it defies imagination, not the quiet of a library or a forest at dusk, but a stillness so profound it's woven into the fabric of space itself. Picture standing in a void where sound doesn't just fade away. It never existed at all. This isn't science fiction. These are the quietest places in the known universe, realms where the absence of noise isn't just eerie, it's a clue to some of the cosmos's greatest mysteries. From the vast, empty stretches between galaxies to the unfathomable depths of black holes, these silent spaces hold stories written in the language of nothingness. And what they reveal might just change how we understand everything. Think about the loudest sound you've ever heard: a thunderclap, a roaring engine, the crash of waves. Now imagine the opposite, a place where those vibrations simply don't travel, where the laws of physics conspire to keep the universe mute. It's not just about the lack of sound, it's about what that silence means. In the vacuum of space, there's no air to carry sound waves, but that's only the beginning. Some corners of the cosmos take quiet to an extreme even scientists struggle to comprehend. These are environments so alien, so utterly devoid of the noise we're used to, that they force us to rethink how energy, matter, and even time itself behave. What if I told you that the quietest places in the universe aren't just empty, they're teeming with hidden activity? Beneath the surface of that perfect silence, particles flicker in and out of existence, gravitational waves ripple unseen, and black holes devour light itself without a whisper. This is where the universe's most profound secrets hide, in the gaps between what we can hear and what we can only theorize. Over the course of this journey, we'll venture into these soundless realms, uncovering how scientists measure silence in space, why some regions are quieter than others, and what these cosmic quiet zones teach us about the nature of reality. The silence out there isn't just absence, it's a message, and we're just beginning to listen. The silence of space isn't just an absence, it's a fundamental feature of the cosmos. Here on Earth, sound travels as waves, pushing air molecules together in a chain reaction we perceive as noise. But in the vacuum between stars, there's nothing to push. No air, no water, not even the thinnest gas to carry a whisper. That's why astronauts floating outside the International Space Station wouldn't hear a supernova exploding nearby. No matter how cataclysmic the event, sound simply has no way to reach them. Yet even in this universal hush, some places take silence to another level. Take the voids between galaxy clusters, for example. These are regions so empty they make the blackness of space seem crowded. Stretching millions of light years across, they contain fewer atoms per cubic meter than the best artificial vacuums we've ever created on Earth. If you could stand in one of these cosmic deserts, you wouldn't just experience silence, you'd be surrounded by a near-total absence of anything that could ever make noise. No stars humming, no solar winds hissing, not even the faint crackle of background radiation. Just pure, unbroken stillness. But here's the paradox: this perfect quiet isn't really empty. Quantum physics tells us that even in the deepest vacuum, particles flicker in and out of existence like static on a cosmic scale. These fleeting disturbances are too faint to ever form sound, but they're proof that true silence is impossible. Even black holes, those infamous devourers of light and sound, aren't completely mute. Their immense gravity warps spacetime itself, sending out ripples we can detect as gravitational waves, a kind of cosmic vibration that doesn't need air or matter to travel. Measuring silence in space isn't about listening, it's about detecting absence. Astronomers use instruments like radio telescopes to map the voids where electromagnetic signals drop to near zero. These quiet zones aren't just curiosities, they're cosmic laboratories. Without the interference of light or sound, they let us study dark matter, dark energy, and the very edges of what we understand about physics. The deeper we probe into these silent stretches, the more we realize the universe speaks loudest when it isn't making a sound. Interstellar space isn't just quiet, it's the closest thing the universe has to a perfect soundproof room. Out here, between the scattered stars, the density of matter drops to just a few atoms per cubic meter. To put that in perspective, the air you're breathing right now contains more than 1 billion times as many molecules in the same space. In this near-perfect vacuum, sound waves have nothing to push against, no medium to travel through. Even the most violent cosmic events, exploding stars, colliding black holes, the birth cries of new galaxies, are utterly silent here. When the Voyager probes ventured beyond our solar system, their instruments picked up something astonishing, the sound of almost nothing. The recordings are haunting, a faint hiss of cosmic background radiation, the occasional pop of a stray particle, but otherwise a stillness so profound it feels almost unnatural. These spacecraft, now humanity's farthest-flung messengers, have given us our first true auditory snapshot of the void, and what they've revealed is a silence deeper than anything we could simulate on Earth. But this silence isn't just emptiness, it's a frontier. For future interstellar travelers, the absence of sound would be the least of their challenges. Without the constant hum of a planet or the vibrations of a ship's engine, the psychological weight of that silence could be overwhelming. Astronauts on the International Space Station report that the quiet of space is one of the most surreal aspects of being in orbit. Now imagine that quiet stretching for years, decades, even centuries. The mental toll of such isolation is something we're only beginning to understand. And then there's the mystery of dark matter. This invisible substance makes up most of the universe's mass, yet it doesn't interact with light or sound in any way we can detect. Could the profound silence of interstellar space hold clues about its nature? Some scientists theorize that the voids between stars might be where dark matter's influence is most apparent, subtly warping the fabric of space in ways we're only now learning to measure. The quieter the environment, the easier it might be to spot the faintest cosmic whispers, ripples in space-time, the echoes of ancient collisions, or even signs of physics beyond our current understanding. What makes interstellar space so fascinating isn't just the absence of noise, but what that absence reveals. In the silence, we find a canvas for the universe's most delicate phenomena, a place where the slightest disturbance could rewrite our understanding of reality. The next time you look up at the night sky, remember, the stars aren't just distant points of light. They're islands in an ocean of quiet so vast, so profound, that it challenges everything we think we know about sound, space, and the nature of existence itself. The moon's silence isn't just eerie, it's a scientific marvel. Unlike Earth, where sound bounces through air, water, and even solid ground, the lunar surface exists in a perpetual state of quiet. Without an atmosphere to carry vibrations, the moon is the ultimate soundproof room. Apollo astronauts reported an almost surreal stillness. Their footsteps kicking up dust made no noise, their tools clattering against rocks fell utterly silent. Even their own voices, trapped inside their helmets, couldn't escape into the void. But this silence became an unexpected gift for science. During the Apollo missions, astronauts placed seismic detectors on the moon's surface, instruments so sensitive they could pick up tremors from meteorite impacts hundreds of miles away. Back on Earth, our planet's constant hum, ocean waves, shifting tectonic plates, even human activity drowns out faint vibrations. On the moon, though, there's no background noise to interfere. Those detectors revealed a world alive with subtle quakes, some caused by the moon's crust cooling and contracting, others by Earth's gravitational pull. The quieter the environment, the clearer the signals, and the more we learned about our closest celestial neighbor. Now imagine harnessing that silence for cutting-edge research. Future lunar bases could take advantage of the moon's natural acoustic isolation to conduct experiments impossible on Earth. Think of ultra-sensitive gravitational wave detectors, free from the rumble of trucks or the whisper of wind. Or radio telescopes on the far side of the moon, shielded from Earth's electromagnetic chatter, listening for the faintest signals from the early universe. The moon's quiet isn't just emptiness, it's a blank slate for discovery. Yet there's a twist. Even in this near-perfect silence, the moon isn't completely soundless. Those seismic experiments picked up something unexpected. Tiny, rhythmic vibrations caused by temperature changes as the lunar surface swings between scorching daylight and freezing night. These moonquakes are so faint you'd need sensitive equipment to detect them, but they prove that even the quietest places in the solar system have their own hidden rhythms. What does this mean for us? The moon's silence is more than a curiosity. It's a reminder of how much we rely on sound to understand our world. On Earth, noise is a constant. On the moon, its absence reveals secrets we'd never hear otherwise. As we plan for long-term lunar missions, we're not just learning to live with silence, we're learning to listen to it. And what we hear could reshape our understanding of everything from planetary formation to the fabric of spacetime itself. Nebulas might look like swirling storms of color in telescope images, but step inside one, and you'd find something unexpected silence. These colossal clouds of gas and dust where stars are born are among the quietest places in the universe, not because they're empty, but because their material is spread so thin. Sound needs particles to travel, and in a nebula, those particles are often light years apart. The result, a cosmic nursery where the violent birth of stars happens in near total hush. Take the Orion Nebula, for example. From afar, it's a brilliant tapestry of light, but deep inside, the density of gas is still 1,000,000 times thinner than Earth's atmosphere. If you could float there, the crash of colliding stellar material, the roar of newborn stars igniting, none of it would reach your ears. The energy is there, but without enough molecules to carry the sound, it dissipates into nothingness. This eerie quiet isn't just a curiosity, it's a critical part of how stars form. In the absence of disruptive noise, gravity can work undisturbed, slowly pulling gas and dust together until the pressure sparks fusion. Astronomers study these silent zones like detectives, piecing together a crime scene where the witnesses never made a sound. By measuring the faint whispers of radio waves and infrared light, they've discovered something surprising. Not all nebulas are equally quiet. Dense, turbulent ones like the Carina Nebula have more sound, not in the way we hear it, but in the form of pressure waves rippling through the gas. In contrast, the quieter nebulas, like the delicate filaments of the Veil Nebula, act like cosmic incubators, their stillness allowing delicate structures to coalesce without being torn apart. And then there's the mystery of the silent zones, pockets within nebulas where even the usual faint vibrations of star formation seem to vanish. Some scientists believe these areas could be where planets begin to take shape, their future solar systems growing in perfect stillness. It's a paradox. The quieter the nebula, the more likely it is to harbor the chaos of creation. The next time you see a Hubble image of a glowing nebula, remember, you're not just looking at a pretty cloud. You're seeing a soundproof room where the universe builds its next generation of stars, one silent collapse at a time. Black holes don't just bend light, they unravel sound itself. Picture the most powerful speaker in the universe blasting music directly into a black hole's event horizon. No matter how deafening the noise, not a single note would escape. That's because the gravitational pull near a black hole is so extreme. It stretches sound waves beyond recognition, warping their frequencies into something unrecognizable before they're torn apart completely. This isn't just silence, it's the total annihilation of vibration as we know it. The physics behind this cosmic muting is as fascinating as it is counterintuitive. Sound travels as waves, relying on particles to bump into one another. But near a black hole, spacetime itself becomes so distorted that these waves get spaghettified, stretched into infinite thinness like cosmic taffy. Even if particles somehow survived the tidal forces, the frequencies would be redshifted so severely they'd vanish from the detectable spectrum. It's as if the black hole isn't just swallowing sound but erasing its very possibility. Scientists simulate these conditions in labs using ultra-cold quantum fluids, creating artificial event horizons where sound waves mimic the behavior of light near a black hole. In these experiments, researchers have observed something eerie. Sound doesn't just disappear, it splits. Some waves plunge into the simulated horizon while others escape as ghostly echoes, a phenomenon that mirrors theoretical predictions about Hawking radiation. These simulations suggest that black holes might not be the perfect silencers we once thought. The implications go beyond acoustics. If sound can leave traces near a black hole's edge, it challenges our understanding of quantum gravity. Some theories propose that the stretched remnants of sound waves could carry information about what's inside the singularity, clues encoded in frequencies, so low they'd take longer than the age of the universe to vibrate once. Other models suggest that the silence of black holes isn't absolute but layered, with quantum vibrations humming just beyond our current ability to detect them. What makes this silence so profound isn't just the absence of noise, it's the questions it forces us to ask. If black holes truly destroy sound, what does that mean for the conservation of energy? Could their eerie quiet hide the signatures of other dimensions or undiscovered physics? Every time we push our instruments closer to these cosmic voids, we're not just listening for what's there. We're listening for what isn't, and why that absence might be the most important message of all. Cosmic voids are the universe's grandest silent spaces, not just gaps between galaxies, but sprawling regions so vast they could swallow entire superclusters without a trace. Picture a bubble hundreds of millions of light-years wide, its walls lined with galaxies like glittering specks, while inside there's almost nothing. No stars, no planets, not even enough gas to fill a thimble. These voids aren't just quiet, they're the closest thing the cosmos has to absolute nothingness. How do these enormous empty rooms form? The answer lies in the universe's earliest moments. After the Big Bang, matter wasn't spread evenly. Some regions had slightly denser clumps, while others were almost bare. Over billions of years, gravity amplified these differences, pulling matter into the dense areas to form galaxies and clusters, while the emptier zones stretched into voids. It's like watching water drain from a bathtub. The liquid rushes toward the plug, leaving behind dry patches. Except in this case, the tub is the fabric of spacetime itself, and the process takes eons. But here's the twist: these voids aren't completely empty. Quantum fluctuations ensure that even the deepest vacuum seethes with particles popping in and out of existence. And then there's dark energy, the mysterious force accelerating the universe's expansion. Some scientists suspect voids are where dark energy's influence is strongest, their emptiness acting like cosmic accelerators, stretching spacetime faster than anywhere else. If that's true, then these silent expanses aren't just passive gaps, they're active players in shaping the fate of the universe. The silence of voids isn't just an absence, it's a tool. Astronomers study these regions to map the universe's large-scale structure, like tracing the holes in a cosmic sponge. By measuring how light bends around voids or how galaxies near their edges move, they've uncovered clues about dark matter's distribution and the universe's overall geometry. The quieter the void, the clearer these signals become. Yet the biggest mystery remains: what happens inside them? Could there be isolated stars or rogue planets drifting unseen, untethered to any galaxy? Or stranger still, might voids harbor exotic physics wormholes, extra dimensions, or even other universes hidden where no light or sound reaches? For now, these questions linger in the silence, waiting for the next generation of telescopes to listen. When we peer into a void, we're not just looking at empty space. We're staring into a mirror reflecting the universe's deepest secrets. Deep beneath the Earth's surface, in tunnels lined with concrete and steel, scientists have built a silence so perfect it rivals the emptiness of space itself. These aren't ordinary labs, they're ultra-quiet chambers where even the vibration of a footstep or the hum of a fluorescent light could drown out the universe's faintest whispers. Places like the LIGO Observatory, with its sprawling vacuum tubes stretching for miles, are designed to detect ripples in space-time so subtle they'd make the flutter of a butterfly's wings seem deafening by comparison. To achieve this extreme quiet, engineers employ techniques that border on the surreal. Multi-layered isolation systems suspend delicate instruments like gravitational wave detectors on pendulums within pendulums, effectively creating a quiet within quiet. The walls absorb sound with specialized foam that traps vibrations like a cosmic sponge, while the entire facility floats on massive springs to cancel out Earth's constant tremors. Even the air is removed, creating a vacuum so pure it mimics the interstellar void. The result, an environment where scientists can hear the universe breathing. What have we learned from these temples of silence? The detection of gravitational waves. A breakthrough that earned a Nobel Prize was only possible because LIGO instruments could listen without interference. These waves, generated by collisions between black holes billions of light years away, stretch and compress space-time by less than the width of a proton. In an ordinary lab, that signal would be lost in the cacophony of everyday noise. But in these silent sanctuaries, it's as clear as a bell. The implications go far beyond astrophysics. Ultra-quiet labs are revolutionizing quantum mechanics by allowing researchers to observe particles behaving in ways that defy classical physics. In one experiment, scientists cooled a tiny aluminum drum to near absolute zero, silencing its atomic vibrations until it existed in two places at once, a quantum superposition visible only in the absence of any disruptive energy. Other teams study quantum squeezing, a phenomenon where silence itself becomes a tool to manipulate light and matter at subatomic scales. Perhaps most astonishing is how these labs bridge the cosmic and the microscopic. The same techniques used to shield detectors from Earth's rumble are now helping build unhackable quantum networks and ultra-precise atomic clocks. Some researchers even speculate that the key to unifying gravity and quantum theory might lie in the shared language of vibration or its absence. After all, if space-time can ripple like a drumhead in the cosmos, perhaps the universe's deepest secrets are waiting to be heard in the quietest places we can imagine. These labs prove that silence isn't just emptiness, it's a lens. By stripping away noise, we don't just hear more clearly, we see the universe anew. Every time scientists push these facilities to new extremes of quiet, they're not just building better instruments. They're learning how to listen to the subtle music of reality itself, a symphony played on instruments of nothingness in halls where sound goes to die. Neutron stars are cosmic contradictions, silent on the outside, chaotic at their core. Born from the explosive deaths of massive stars, these ultra-dense remnants pack more mass than our Sun into a sphere barely the size of a city. Their surfaces, smooth as polished metal and devoid of atmosphere, don't just lack sound, they actively suppress it. With gravity 100 billion times stronger than Earth's, even the idea of vibration is crushed into submission. A single pebble dropped onto a neutron star's surface wouldn't make a sound. It would be flattened into silence before it could disturb the eerie calm. Yet this quiet is deceptive. Beneath that silent crust, the star's interior churns with hyperfluid neutrons spinning at near light speed, while magnetic fields so powerful they could strip atoms apart ripple through surrounding space like invisible tsunamis. These fields don't just mute sound, they obliterate the very conditions needed for it. Charged particles caught in a neutron star's magnetic grip are funneled into deadly beams along the poles, emitting X-rays and gamma rays instead of audible noise. It's as if the star has pressed a cosmic mute button on its surroundings, creating a bubble of silence amid the chaos of the universe. Astronomers call this phenomenon magnetic silencing, and it's one of the most extreme examples of physics overriding our everyday expectations. On Earth, we're used to sound traveling through air, water, even solids, but near a neutron star, the rules change entirely. The magnetic fields are so intense they ionize any nearby gas, stripping electrons from atoms and scattering them too thinly to carry vibrations. The result, a zone of perfect quiet stretching light years into space, where even the scream of a supernova would fall on deaf ears. But neutron stars aren't completely silent. Some, called pulsars, emit rhythmic beams of radiation that sweep across space like lighthouse beams, a kind of cosmic Morse code. These pulses aren't sound waves, of course, but if you could translate them into audio, they'd produce a ticking more precise than any atomic clock. The fastest pulsars spin hundreds of times per second, their surfaces rotating at a fraction of light speed without so much as a whisper of friction. It's a reminder that silence in space isn't about stillness, it's about motion so perfectly balanced it leaves no trace. What fascinates scientists most is how neutron stars push matter to its breaking point. Under that silent exterior, protons and electrons have been crushed together so violently they merge into neutrons, creating a state of matter that doesn't exist anywhere else in the universe. Some theories suggest the cores of these stars might contain even stranger materials, quark soup, or free-floating strands of spacetime itself. The only way to study these extremes is by observing the absence they create, the way their gravity bends light without sound, or how their magnetic fields clean the cosmic clock of surrounding noise. The lesson neutron stars teach us is profound. Silence isn't passive. It can be the product of unimaginable forces, a side effect of physics pushed to its limits. Every time we detect a pulsar's steady blink or map the quiet around a magnetar's deadly field, we're glimpsing the universe's ability to balance fury and stillness. These silent giants are more than cosmic oddities, they're laboratories for the impossible, proving that sometimes the loudest truths come wrapped in perfect quiet. Dark matter is the universe's phantom, an invisible sculptor shaping galaxies and cosmic voids without leaving a whisper. Unlike ordinary matter, it doesn't reflect light, emit radiation, or produce sound waves. It doesn't even bump into itself, yet its gravitational pull is so immense that without it, galaxies would fly apart, and the cosmos as we know it wouldn't exist. This silent partner works behind the scenes, bending the paths of stars and stretching the fabric of spacetime, all without making a sound. How do we know it's there if we can't see or hear it? The clues are in the empty spaces. Take galaxy clusters, for example. When astronomers measure how fast stars orbit their centers, they find something strange. The outer stars move just as fast as the inner ones, defying the laws of gravity as we understand them. The only explanation, an unseen mass, a gravitational glue holding everything together. This is dark matter's signature, not a sound, not a flash, but the undeniable tug of something we can't perceive directly. But here's where it gets even stranger. Dark matter doesn't just lurk in galaxies, it defines the quietest places in the universe. Those vast cosmic voids, the empty stretches between galaxy clusters. They're not entirely empty. Dark matter weaves through them like an invisible scaffold, its gravitational influence shaping the distribution of everything else. Without it, those voids would collapse and the universe's large-scale structure would unravel. It's as if the silence of these regions isn't just an absence of noise, it's the fingerprint of something far more profound. Could we ever detect dark matter's sound? Not in the traditional sense. Since it doesn't interact with ordinary matter except through gravity, it doesn't create vibrations we could hear. But scientists are hunting for indirect ways to listen. Some experiments use ultra-sensitive detectors cooled to near absolute zero, waiting for the faintest tick of a dark matter particle colliding with an atom. Others monitor the hum of the universe's oldest light, the cosmic microwave background, for subtle distortions caused by dark matter's gravitational waves. These techniques won't give us sound in the way we think of it, but they might translate dark matter's influence into something we can interpret. The deeper mystery is why dark matter is so silent in the first place. Most theories suggest it's made of particles that barely interact with anything, not even each other. If that's true, then its silence isn't an accident. It's baked into the fundamental laws of physics. But there's a tantalizing alternative. What if dark matter isn't completely silent? Some models propose rare interactions that could produce faint signals, like whispers in a soundproof room. If those exist, future observatories might pick them up, turning the universe's quietest player into something we can finally hear. For now, dark matter remains the ultimate cosmic enigma, a force that shapes the universe without making a sound. Its silence challenges our understanding of physics, pushing us to rethink what matter even is. Every time we map the gravitational ripples in a galaxy or measure the strange motion of stars, we're not just studying dark matter. We're learning to appreciate the power of silence and how the loudest truths in the cosmos might be hiding in what we can't hear. Even in the emptiest corners of the universe, there's a hum, a faint, ceaseless crackling beneath the fabric of reality itself. This is the quantum vacuum, a sea of particles and antiparticles flickering in and out of existence so quickly they defy detection. To call it silent would be a lie. It's more like a static hiss at the edge of perception, a reminder that true emptiness is impossible. But what if we could mute even that? Some theories suggest there might be ways to create pockets of absolute quiet regions where the universe's background buzz is silenced, and for the first time we'd hear nothing at all. The key lies in quantum fluctuations. These aren't just random noise, they're the universe's way of balancing the books. Energy can't be created or destroyed, but it can borrow from the future, manifesting as particle pairs that annihilate almost instantly. This dance of creation and destruction fills every cubic centimeter of space with a faint energy, even in the deepest vacuum. It's why scientists say a perfect vacuum isn't truly empty, it's alive with potential. But recently, physicists have begun asking a radical question. Could we manipulate these fluctuations to create zones of perfect silence? One approach involves something called squeezed light. By tweaking the quantum noise in a laser beam, researchers can redistribute its fluctuations, effectively silencing certain frequencies while amplifying others. It's like turning down the bass in a song until only the faintest high notes remain, except here, the song is the fabric of space-time. In labs, this technique has already been used to cool atoms to near absolute zero, quieting their vibrations until they're barely moving at all. The quieter the system, the easier it is to spot deviations like gravitational waves or the faint signatures of dark matter. But the ultimate test of silence might lie in black holes. Near the event horizon, quantum effects become so extreme that particles are torn apart faster than they can annihilate, leaving behind a faint glow-hawking radiation. Some models suggest that under these conditions, certain frequencies of quantum noise could cancel each other out, creating fleeting pockets of perfect quiet. If true, it would mean the universe's loudest destroyers might also be its best silencers. Yet the most tantalizing possibility comes from theoretical constructs like false vacuums. These are hypothetical regions where the quantum field drops to its lowest possible energy state, freezing fluctuations in place. Here, the universe wouldn't just be quiet, it would be mute, with no energy left to spare for even the tiniest vibration. The catch, entering such a zone could rewrite the laws of physics for everything it touches, like a cosmic reset button. What does this mean for our search for silence? It shows that quiet isn't just the absence of sound, it's a delicate balance of forces, a negotiation between energy and emptiness. The universe may never let us experience true silence, but in trying to find it, we're learning to listen to its subtlest rhythms. And who knows, the day we finally hear nothing at all might be the day we discover everything. Beyond the orbits of Neptune and Pluto, in the frozen outskirts of our solar system, lies a realm so still it makes the vacuum of space seem noisier, the Oort Cloud. Imagine a vast spherical shell of icy objects stretching nearly a light year into the void, so distant that the sun appears as little more than a bright star. Here, in this twilight zone, temperatures hover just a few degrees above absolute zero, and the silence is so profound that even the whisper of a comet's tail is a rare event. This isn't just emptiness, it's a cosmic deep freeze, preserving secrets from the dawn of our solar system. The Oort Cloud's quiet isn't an accident, it's a consequence of its extreme isolation. Unlike the asteroid belt or the Kuiper belt, where objects jostle and collide, the Oort Cloud's icy bodies are spaced so far apart that a traveler passing through might go millennia without encountering another. A single comet might drift undisturbed for millions of years, its orbit tweaked only by the faintest gravitational nudge from a passing star or the tidal pull of the Milky Way itself. This near-perfect stillness makes the Oort Cloud a pristine time capsule. Every chunk of ice and rock here is a relic from the solar system's infancy, unchanged since the era when planets were still forming. What's astonishing is how much this silence reveals. When a comet from the Oort Cloud finally streaks inward, warmed by the sun's faint heat, it carries chemical fingerprints from 4.5 billion years ago. These icy wanderers are like cosmic archaeologists, delivering samples of the primordial material that built our solar system. Their silence, the fact that they've been untouched for eons, means they haven't been contaminated by later events like asteroid impacts or planetary migrations. Studying them is like listening to a recording of the solar system's birth, one that's been kept perfectly preserved in the universe's quietest vault. Yet the Oort Cloud's quiet also poses a challenge. Its remoteness makes it nearly impossible to observe directly. Unlike the Kuiper belt, where telescopes can spot reflected sunlight, the Oort Cloud's objects are too dim and too far away. Instead, astronomers rely on rare comets that get knocked loose from their orbits, falling sunward like messengers from the void. Each one is a clue, but deciphering the full story requires piecing together fragments from an invisible realm. There's a deeper mystery lurking in this silence. Some scientists suspect the Oort Cloud might not be entirely ours. Computer simulations suggest it could contain interstellar interlopers' icy bodies captured from other star systems during the sun's infancy, frozen in place like flies in amber. If true, these silent wanderers could hold secrets not just about our solar system, but about the galactic neighborhood we grew up in. The quieter the Oort Cloud, the more it seems to whisper about connections we're only beginning to understand. The next time you hear about a comet visiting the inner solar system, remember, it's not just a celestial spectacle. It's a break in the silence, a momentary ripple in a sea of stillness that's endured since before the planets took shape. And the more we learn from these icy time travelers, the more we realize the universe's quietest places often speak the loudest. Some worlds orbit so far from their stars that their nights never end, planets drifting in perpetual twilight, where the faintest starlight barely kisses frozen surfaces. These aren't just cold exoplanets, they're cosmic libraries where silence has reigned for billions of years. Take, for example, a super-Earth like Ogle 2505 BLG 390 microlensing event, a frozen rogue wandering so distant from any star that its surface temperature hovers near absolute zero. On such a world, even the atmosphere, if it exists at all, would have frozen solid eons ago, leaving behind a landscape where sound waves have nothing to travel through. No wind howls, no rivers rush, just an unbroken hush stretching across continents of ice. Yet this very silence raises a tantalizing question: could life persist in such stillness? Earth's extremophiles, organisms thriving in deep-sea vents or Antarctic ice, prove that life clings in the unlikeliest places. But these creatures still rely on energy gradients, chemical reactions, or geothermal heat. On a distant exoplanet cut off from stellar warmth, what energy source could fuel biology? Some astrobiologists speculate about cold metabolism, where life operates in ultra-slow motion, powered by rare radioactive decay or the faint tidal flexing of a moonless world. Others imagine ecosystems huddled around subsurface volcanoes, where whispers of heat create isolated oases in an otherwise silent globe. The challenge isn't just temperature, it's time. Planets in these distant orbits likely formed far from their stars' habitable zones, missing the volatile, rich materials that seed atmospheres and oceans. Without geologic activity to recycle nutrients or magnetic fields to deflect radiation, their surfaces may be sterile deserts, but beneath the ice, things get interesting. Moons like Europa and Enceladus show us that liquid water can persist under frozen shells, heated by tidal forces. A silent exoplanet with a similar subsurface ocean might harbor life that never knows daylight or sound, its existence detectable only through faint biosignatures escaping via cryovolcanoes. Here's the paradox: the quieter the exoplanet, the harder it is to study. Traditional methods like transit photometry or radial velocity struggle to detect worlds orbiting at hundreds of astronomical units. Even direct imaging, which captures exoplanets by their infrared glow, falters when objects are this cold. Future telescopes like NASA's Habitable Worlds Observatory might change that, but for now, these silent orbits remain cosmic blind spots. What makes them fascinating isn't just the possibility of life, but what their silence teaches us about habitability limits. If biology can spark in such frozen quiet, it redefines the very meaning of living world. And if it can't, these planets become something equally profound. Natural laboratories where we learn why sound, whether from crashing waves or buzzing ecosystems, might be a universal signature of vitality. The universe's quietest worlds aren't just oddities. They're mirrors reflecting how much we still don't understand about the delicate interplay of energy, chemistry, and the faintest whispers of life. What if silence isn't just the absence of sound, but the absence of everything, not empty space, not darkness, not even the fabric of reality itself? This is the enigma of the pre-Big Bang universe, a state so fundamentally alien that even calling it silent might miss the point entirely. Without space-time, there are no vibrations to carry sound, no particles to collide, no medium for anything to disturb. It's a silence deeper than any black hole or cosmic void, a nothingness that defies the very concept of quiet because silence, as we understand it, couldn't exist yet. Theoretical physicists grapple with this paradox daily. Some propose that the pre-Big Bang universe wasn't empty at all but seething with potential, a quantum foam where tiny bubbles of spacetime flickered in and out of existence. In this view, the silence before creation might have been a chaotic hum of virtual particles, a static of unmanifested energy waiting for the right conditions to explode into being. Others suggest a cyclical model where our universe is just the latest in an endless series of expansions and contractions. If that's true, the pre-Big Bang era wasn't silent. It was the aftermath of a previous cosmos collapsing into a singularity, a cosmic exhale before the next breath. Then there's the idea of nothingness itself. Philosophers and physicists alike debate whether true nothing, no space, no time, no physical laws, is even possible. Some argue that the laws of quantum mechanics prevent absolute emptiness, meaning even the void before time might have had a subtle, underlying structure. Imagine trying to describe the quiet of a room that doesn't exist, with no walls, no air, and no one to listen. That's the challenge cosmologists face when they theorize about the pre-Big Bang universe. The most radical theories come from quantum gravity research, where scientists speculate that spacetime might emerge from something even more fundamental, a network of entangled particles or a sea of abstract mathematical relationships. In these models, the silence before creation isn't passive. It's a computational blank slate, a state where the universe's code hasn't yet begun to run. It's as if the cosmos was a symphony waiting for its first note, with silence not as emptiness but as potential energy coiled tight. What does this mean for our understanding of silence? If the universe began from absolute nothingness, then sound, and its absence are inventions of the Big Bang itself. But if something always existed, even if it defies our current physics, then silence takes on a new dimension, not just the lack of noise, but a canvas for reality's first strokes. Every time we peer deeper into cosmic microwave background or simulate quantum fluctuations, we're not just studying the past, we're listening for echoes of a silence so profound it birthed everything we know. Galaxy clusters aren't just collections of stars, they're cosmic soundproofing, bending and swallowing vibrations in ways that leave eerie silent patches across the universe. These acoustic shadows form when sound waves traveling through the sparse gas between galaxies hit a massive cluster's gravity. Like light bending around a lens, the waves get distorted, diverted, or absorbed entirely, leaving behind pockets of unnatural quiet. It's as if the universe has its own mute button, and these clusters are pressing it. But here's the twist: these silent zones aren't just empty. They're cosmic X-rays, revealing the invisible scaffolding of dark matter that holds clusters together. When astronomers map where sound disappears, they're actually tracing the gravitational pull of matter we can't see. The quieter the shadow, the stronger the tug, a paradox where silence speaks volumes. Take the Perseus cluster, for example. Its superheated gas should hum with pressure waves from exploding stars, but certain regions are mysteriously hushed. The reason dark matter's grip is so strong there, it stifles vibrations before they can travel far. These acoustic shadows also act as time capsules. Sound waves from the early universe, called baryon acoustic oscillations, left imprints in the distribution of galaxies like ripples frozen in a pond. By studying where those ripples vanish, scientists reconstruct the universe's expansion history with startling precision. It's akin to listening for echoes in a canyon and realizing the quiet spots tell you more than the noise. Yet the biggest mystery lurks in the quietest shadows. Some patches of silence are deeper than current physics can explain, suggesting forces beyond our understanding. Perhaps exotic dark energy interactions or undiscovered particle fields. Future telescopes like the Square Kilometre Array aim to listen to these silent zones with unprecedented sensitivity, turning cosmic quiet into a new kind of signal. The lesson here is counterintuitive. In space, silence isn't just the absence of sound. It's a footprint, a clue, a fingerprint of the unseen. Every time an acoustic shadow defies expectations, it's not just hiding something, it's inviting us to rethink what we know about the universe's hidden symphony. Scientists don't just listen to the universe, they weaponize silence. Think of the most sensitive microphone ever built. Then imagine placing it in a room where every whisper of interference has been meticulously erased. That's the essence of modern observatories, where the quest to hear cosmic whispers demands silencing everything else. Radio telescopes like the Atacama Large Millimeter Array perch on high deserts, their dishes shielded from Earth's radio chatter by miles of thin, dry air. Gravitational wave detectors like LIGO bury their lasers in vacuum chambers, suspended by mirrors so isolated that passing trucks and distant ocean waves could drown out the birth cries of black holes. These aren't just instruments, they're temples of quiet, engineered to amplify the faintest murmurs of reality. Take neutrinos, for example, ghostly particles that pass through planets like they're not even there. Detecting them requires laboratories buried deep underground, where rock layers mute the noise of cosmic rays. The Ice Cube Neutrino Observatory in Antarctica uses a cubic kilometer of glacial ice as both detector and soundproofing, waiting for the rare flash of light when a neutrino collides with an atom. It's like trying to hear a pin drop in a hurricane by building a room where the storm doesn't exist. But the real frontier lies in pushing silence further. Quantum sensors now cool atoms to within a fraction of absolute zero, quieting their thermal jitter until they can measure space-time distortions smaller than an atomic nucleus. Some prototypes even use entangled particles to cancel out noise before it happens, a cosmic version of noise-canceling headphones for the fabric of reality itself. The goal, to catch the sound of a black hole's first breath, the tremor of a higher dimension brushing against our own, or the echo of the universe's infancy encoded in gravitational waves. What makes this possible isn't just technology, it's a radical shift in perspective. For centuries, astronomy relied on light. Now we're learning to listen. When two black holes collided 13 billion years ago, they sent ripples through spacetime that reached Earth in 2015 as a faint chirp, a signal so quiet it took decades of engineering to hear it. That detection didn't just confirm Einstein's prediction, it opened a new sense for exploring the cosmos. The next targets, the murmurs of neutron stars spinning in perfect sync, the low-frequency hum of supermassive black holes merging, even the theoretical crackle of cosmic strings, defects in spacetime left over from the Big Bang. Each requires silencing Earth's noise on an unprecedented scale. Future projects like the Einstein telescope plan to bury detectors underground and in space, creating a symphony of silence where the universe's softest notes finally rise above the static. Here's the astonishing truth: the quieter we make our machines, the louder the cosmos becomes. What we once dismissed as emptiness is now a canvas of hidden vibrations, each carrying secrets about dark matter, quantum gravity, and the origins of everything. The challenge isn't just building a better microphone, it's learning to listen in a universe that never stops speaking, even when it's silent. Mars isn't just another planet, it's a world where sound itself behaves strangely. With an atmosphere only 1% as dense as Earth's, the red planet muffs noises like a cosmic pillow, turning what should be sharp cracks into distant thuds. When NASA Perseverance rover recorded the first audio clips from Mars, scientists were stunned. The hum of the rover's wheels rolling over gravel, the whir of its drill biting into rock, all of it sounded eerily muted, as if someone had turned down the volume on reality itself. Even the wind, which can whip dust into towering storms, registers as little more than a whisper. These recordings aren't just curiosities, they're acoustic fingerprints revealing Mars' secrets. The way sound travels or doesn't exposes details about atmospheric pressure, temperature, and even the planet's geology. High-pitched noises like the laser pulses Perseverance uses to zap rocks fade almost instantly, while lower tones linger slightly longer, creating a soundscape unlike anything on Earth. It's as if Mars has its own peculiar audio filter, one that could reshape how future colonists communicate. Without the dense air we're used to, even shouted conversations might sound stifled, forcing settlers to rely on tech like bone conduction headsets or vibration-based systems. But the silence of Mars goes deeper than physics. Imagine living in a place where footsteps barely echo, where storms rage in near silence, and where the absence of birds, insects, or rustling leaves leaves the landscape unnervingly still. Earth's soundscape is so ingrained in our psychology that its absence could trigger a phenomenon called sensory deprivation stress. Polar researchers and astronauts in isolation already report discomfort with prolonged silence, describing it as oppressive or surreal. On Mars, that silence wouldn't be temporary, it would be permanent, broken only by mechanical noises or the occasional crack of a landing spacecraft. Yet there's a flip side. This very quiet could become a scientific asset. Without Earth's constant background rumble, seismometers on Mars detect quakes far more clearly, revealing the planet's inner structure. Future observatories could capitalize on the silence too, listening for cosmic phenomena drowned out by our noisy home planet. And for some, the stillness might even offer a kind of peace, a respite from the sensory overload of modern life. The challenge lies in adaptation. Early Martian habitats might pump in artificial ambient noise, forest sounds, ocean waves, or even simulated cafe chatter to stave off the psychological weight of silence. But long-term, colonists could develop new norms, finding beauty in the stark acoustics of their new world. After all, Mars isn't truly silent. It's just speaking a language we're still learning to hear. The roiling clouds of Jupiter and Saturn scream with hurricane-force winds, their storms loud enough to shake the very fabric of their atmospheres, but dive deep enough and something strange happens. The cacophony fades. Scientists suspect that beneath these gas giants' turbulent outer layers, their crushing pressures create zones of near-perfect silence where sound waves can't even form. It's as if the planets have built in mute switches, their own gravity smothering noise before it can travel. Picture descending into Jupiter's depths. The first 1,000 kilometers are a maelstrom of ammonia crystals and hydrogen swirling at supersonic speeds. But go deeper, where pressures exceed 1,000,000 times Earth's surface level, and the rules change. Hydrogen gas compresses into a bizarre metallic state, a fluid that conducts electricity like copper yet stifles vibrations like a cosmic sponge. In this realm, collisions between atoms happen so quickly and densely that sound waves get stuck, their energy dissipating almost instantly. Models suggest that at certain depths, the silence could be so profound that even the violent churning of the planet's core wouldn't make a whisper. Saturn's interior might be even stranger. Its lower pressure environment allows for a thicker layer of molecular hydrogen, which could act like a soundproofing blanket over the inner layers. Some simulations indicate that Saturn's deep interior, where helium rain falls through liquid metallic hydrogen, could be one of the quietest natural places in the solar system. The very forces that make gas giants so noisy on the outside, their immense gravity and pressure, might be what silences them within. What does this mean for planetary science? These silent zones could be time capsules, preserving clues about how gas giants formed. Earth's geology gets reshaped by plate tectonics and erosion, but deep inside Jupiter, conditions haven't changed much in 4.5 billion years. If we could probe those soundless depths, we might find traces of the primordial solar system isotope ratios, exotic materials, or even pockets of heavier elements that sank to the core during the planet's infancy. The quieter the zone, the more pristine the evidence. Yet the biggest mystery isn't just what's silent, it's what isn't. Some theories predict that gas giants hum at ultra-low frequencies, their cores vibrating like colossal subwoofers from gravitational interactions with their moons. Jupiter's resonance with Io, for example, might generate oscillations we could one day detect with advanced seismometers. If so, these planets aren't completely mute, they're broadcasting in a register we're only beginning to hear. The deeper lesson here is about balance. Gas giants are cosmic paradoxes. Their surfaces scream with violence, while their hearts may beat in near-perfect quiet. Understanding that duality doesn't just reveal how planets work, it hints at how chaos and stillness can coexist across the universe. Whether in the eye of a storm or the heart of a giant, silence isn't just emptiness, it's a hidden dimension of physics waiting to be explored. The cosmic microwave background isn't just radiation, it's the fossilized echo of the universe's first sound. Stretching back over 13 billion years, this faint glow is the aftermath of the Big Bang's deafening roar, stretched and cooled into near silence by the expansion of space itself. What began as a searing blast of energy has faded into a whisper so faint that if our ears could hear it, it would register as little more than a hiss, quieter than falling snow. Yet within this cosmic static lies a treasure map of the early universe, encoded in fluctuations smaller than 1 part in 100,000. These tiny variations, warmer and cooler patches no larger than a quarter of the sky, tell a story of pressure waves rippling through the infant cosmos. In the first 380,000 years after the Big Bang, the universe was so dense that light couldn't travel far before bouncing off charged particles, creating a plasma as viscous as syrup. Sound waves propagated through this soup, compressing matter in some regions and rarefying it in others. When the universe finally cooled enough for atoms to form, releasing light to travel freely, those waves froze in place, imprinting their pattern onto the CMB like fingerprints on glass. Scientists decode this pattern using instruments like the Planck satellite, which map the CMB's temperature variations with precision finer than a millionth of a degree. The resulting images resemble a cosmic fingerprint, swirls and speckles that reveal the universe's composition, shape, and even its ultimate fate. The quietest spots in these maps, where fluctuations are smoothest, correspond to voids where dark energy's repulsive force dominates. Meanwhile, the slightly louder clusters hint at the gravitational seeds that would one day grow into galaxies. It's as if the universe left us a voicemail in a language of heat and silence, waiting to be translated. But the CMB's silence isn't just a relic, it's a tool. By studying how its waves polarized, researchers confirmed the existence of primordial gravitational waves, ripples in space-time from the universe's explosive birth. Other teams hunt for B-modes, twisted patterns in the CMB's polarization that could signal cosmic inflation's fingerprints. The quieter the background noise, the clearer these signals become, like spotting a single candle flicker in a darkened room. Future observatories, like the Simons Observatory in Chile, aim to push this silence even further, probing the CMB for whispers of quantum gravity or hidden dimensions. What makes this cosmic hum so extraordinary is its duality. To us, its silence a microwave murmur indistinguishable from the static of an old television. But to the universe, it's a shout, a final echo of creation's first moments. Every time astronomers refine their measurements, they're not just listening to the past. They're hearing the blueprint of everything written in the language of near-nothingness. Silentium, the theoretical state of absolute silence, isn't just the absence of sound, it's the absence of vibration itself. Imagine a pocket of the universe where even the quantum hum of particles flickering in and out of existence falls still, where space-time itself holds its breath. This isn't science fiction. It's a frontier of physics that forces us to confront whether true silence is even possible. The laws of thermodynamics tell us energy can never be fully destroyed, only transformed. So how could a place exist where every ripple of motion ceases? The answer might lie in the coldest corners of reality. Near absolute zero, atoms slow to a near standstill, their thermal jitter quieted to a whisper. In labs, scientists have chilled matter to within a billionth of a degree above zero, creating conditions where sound waves freeze mid-vibration. But even this isn't Silentium. Quantum mechanics insists that particles must retain a faint residual energy, the so-called zero-point energy, a fundamental buzz that can't be silenced. To achieve true quiet, we'd need to bypass physics itself, creating a region where even quantum fluctuations are muted. Some theories suggest this could happen in the heart of a black hole's singularity, where the laws of physics as we know them break down entirely. Yet the paradox runs deeper. If Silentium existed, it would defy the Heisenberg uncertainty principle, which states that particles can never be perfectly at rest. Even in a vacuum, virtual particles pop into existence, borrowing energy from the future to sustain their fleeting lives. To silence them would require rewriting quantum theory or discovering a loophole. One radical idea involves negative energy, a hypothetical state that could cancel out these fluctuations. If harnessed, it might create a bubble where vibrations cease, like pressing cosmic noise canceling headphones against the fabric of reality. The implications would shatter our understanding of existence. Thermodynamics relies on the constant exchange of energy. A Silentium zone would be a thermodynamic dead end, a place where entropy stalls. Could such a region exist naturally? Some cosmologists speculate that the pre-Big Bang universe, or the far future as heat death approaches, might resemble this eerie stillness. Others suggest Silentium could be engineered, using technologies far beyond our grasp to sculpt space-time into perfect quiet. But here's the haunting twist. If we ever found Silentium, we wouldn't be able to observe it. Detection requires interaction, light, sound, or some form of energy exchange. A truly silent region would be invisible, untouchable, a ghost in the cosmic machine. It would exist as a shadow, known only by the absence of everything else. The pursuit of absolute silence isn't just about pushing physics to its limits. It's about asking whether the universe ever stops speaking and what it means if the answer is yes. Silence isn't just an absence, it's a force, on Earth, true quiet is nearly impossible to find. Even in the most remote deserts or deepest caves, there's always something: the rustle of wind, the drip of water, the faint hum of your own heartbeat. But in space, silence takes on a new dimension. Astronauts aboard the International Space Station report that the quiet outside their windows is unlike anything on Earth, a void so profound it feels almost physical. Without air to carry sound, the usual auditory cues of life vanish, leaving behind a stillness that can be as unsettling as it is awe-inspiring. Studies of long-duration spaceflight reveal just how deeply this silence affects the mind. In isolation, experiments like NASA HIC's program, where crews live for months in a Mars-like habitat, participants report that the lack of ambient noise becomes psychologically oppressive over time. The brain, wired to interpret sound as a sign of life and activity, starts to rebel against the quiet. Some astronauts describe hearing phantom noises, false alarms of ringing phones or distant voices, a phenomenon known as auditory pareidolia, where the mind manufactures sound to fill the void. Others struggle with a creeping sense of detachment, as if the silence erodes their connection to reality itself. The implications for deep space travel are profound. A mission to Mars would expose astronauts to months of near-total silence, broken only by mechanical noises or recorded messages from Earth. Without the familiar soundtrack of a living planet, birdsong, rustling leaves, even the white noise of a bustling space station, mental fatigue could set in faster than we expect. Polar researchers wintering in Antarctica, another environment of extreme quiet, report similar challenges. The monotony of silence amplifies small stresses, turning minor irritations into existential frustrations. In space, where every decision carries life or death stakes, that psychological strain could be dangerous. Yet silence isn't inherently harmful. Monasteries and meditation retreats have long harnessed quiet for focus and clarity. The difference lies in control. On Earth, we can break the silence whenever we choose a spoken word, a played song, the opening of a window. In space, the quiet is inescapable, a constant reminder of how far removed you are from everything familiar. Future missions might need to simulate Earth's soundscape artificially, using recordings of rain or cafe chatter to stave off sensory deprivation. Some proposals even suggest soundscaping spacecraft with dynamic audio environments that shift to match crew morale, using rhythm and frequency to subconsciously ease stress. The deeper question is whether humans can adapt to cosmic silence, not just endure it, but learn to thrive in it. Early submariners faced similar doubts about living in steel tubes beneath the ocean, yet over time they developed rituals and routines to cope. Spacefarers might discover their own ways to reframe the quiet, hearing in it not emptiness but a kind of cosmic invitation. After all, silence is the native state of the universe. To explore the stars, we may need to become comfortable with listening to nothing at all, and in that nothingness we might finally hear ourselves. The universe should be loud. With billions of galaxies, each home to countless stars and planets, the cosmic cacophony of intelligent life ought to be deafening. Yet when we point our telescopes skyward, we're met with silence, an eerie absence of signals that defies expectation. This is the Fermi paradox in a nutshell. If alien civilizations exist, why haven't we heard them? But what if we've been listening wrong? Sound, as we understand it, requires a medium, air, water, even solid ground, to carry vibrations. In space's near-perfect vacuum, traditional sound waves don't travel, so we've focused on radio and light signals instead. Yet this assumes alien species communicate as we do, using tools recognizable to 20th century human technology. Imagine an advanced civilization that abandoned radio millennia ago, transitioning to something far more exotic. neutrino pulses, quantum entanglement, or even gravity waves themselves. Their language might ripple through space-time in ways our instruments can't yet detect, leaving their conversations hidden in plain silence. Then there's the possibility of deliberate quiet. Some theorists suggest mature civilizations might avoid broadcasting their presence, adhering to a cosmic version of radio silence to evade potential threats. Picture a galaxy where every intelligent species learns to whisper, their signals so tightly focused or encrypted that they blend into the background noise of the universe. Others might communicate through slow, patient bursts, sending messages stretched over centuries to conserve energy, their meaning lost in our brief observational windows. But the most intriguing idea flips the paradox entirely. What if we're the loud ones? Human-made radio signals have only leaked into space for about a century, a blink in cosmic time. An alien civilization just a few hundred light-years away might not have detected us yet, or they might consider our primitive transmissions unworthy of response. In a universe billions of years old, we could be the newcomers, our shouts lost in a sea of ancient, fading echoes. The silence might not be empty at all, just tuned to a frequency we're only beginning to imagine. As we develop tools to detect gravitational waves or quantum vibrations, we might finally catch the murmur of civilizations talking in ways we're only starting to understand. The universe isn't necessarily silent. We might just need to learn how to listen. The hunt for cosmic silence is about to get a major upgrade. Scientists are developing quantum microphones so sensitive they could detect the gravitational hum of a black hole's spin or the faint tremor of a neutron star's crust cracking under pressure. These aren't your ordinary microphones, they're devices chilled to near absolute zero, where atoms slow enough to sense vibrations smaller than a proton. Imagine trying to hear a snowflake land on the surface of a pond from orbit. That's the level of precision we're talking about, and it's opening doors to sounds we never knew existed. One of the most anticipated projects is the Einstein telescope, a next-generation gravitational wave detector set to be buried underground to shield it from Earth's rumble. Unlike LIGO, which caught the first gravitational waves in 2015, this observatory will be 10 times more sensitive, capable of hearing black hole mergers from the universe's earliest epochs. Its triangular design, with laser arms stretching 6 miles long, will act like a cosmic stethoscope, listening for the faintest pulses in space-time. The goal, to catch the ringing of primordial black holes or even the echoes of cosmic strings, theoretical defects in space-time left over from the Big Bang. But hardware is only half the story. AI-driven noise filters are revolutionizing how we process cosmic data. Traditional methods struggle to separate faint signals from background static, but machine learning can now identify patterns invisible to human analysts. At the Square Kilometre Array, a massive radio telescope network under construction, AI will sift through exabytes of data to pick out whispers from distant pulsars or the elusive signatures of dark matter particles colliding. It's like trying to hear a single voice in a stadium crowd, except the stadium is the universe, and the voice might be a message from another dimension. Then there's the wild card, quantum entanglement sensors. These devices exploit the bizarre property of entangled particles to cancel out noise before it even reaches the detector. In theory, they could create pockets of artificial silence so pure that even the quantum jitter of atoms is suppressed. If successful, they might let us hear phenomena we've only dreamed of, like the low-frequency hum of supermassive black holes merging or the vibrational fingerprints of extra dimensions. The most exciting part, we're not just building better listeners, we're redefining what silence even means. Future missions like ESA's LISA will float lasers in space to detect gravitational waves at frequencies too low for ground-based instruments. Others propose using the Moon as a giant soundproof chamber, placing telescopes on its far side to escape Earth's radio chatter. Each innovation peels back another layer of cosmic noise, revealing a universe far more talkative than we ever imagined. What awaits us in these uncharted quiet zones may be the murmurs of alien megastructures, the hum of undiscovered particles, or even the faint pulse of a universe beyond our own. One thing's certain, the quieter our tools become, the louder the cosmos gets, and the next breakthrough might not come from what we hear, but from what we finally stop ignoring. Humanity has always been loud. Our cities hum, our machines roar, and our radio signals leak into space like a beacon announcing our presence. But as we reach further into the cosmos, we face an ethical dilemma. Do we have the right to shatter the universe's quietest places? Imagine a future where spacecraft rumble through interstellar voids, where mining operations on silent moons kick up vibrations, or where orbiting satellites broadcast endless data streams into regions that have known nothing but stillness for billions of years. The question isn't just about noise, it's about whether some corners of space deserve to remain untouched, preserved as sanctuaries of silence. Science relies on quiet. The same way light pollution obscures our view of the stars, sound pollution, or more accurately, vibration pollution, could drown out faint cosmic signals we've only just begun to detect. Gravitational wave observatories like LIGO need near-perfect stillness to catch ripples from colliding black holes. Future telescopes hunting for alien civilizations or quantum echoes from the Big Bang would struggle if humanity's noise flooded the cosmic bandwidth. It's not just about volume, it's about contamination. A single errant transmission or the mechanical hum of a distant probe could skew data for generations. But the argument goes beyond practicality. Silence has cultural and philosophical value. Indigenous communities on Earth have long revered quiet places as sacred, zones where the absence of sound fosters reflection and connection to something greater. If we accept that untouched forests or deserts deserve protection, shouldn't the same apply to the pristine quiet of a Martian polar cap or the soundless depths of a galactic void? These environments aren't just empty, they're time capsules holding clues to the universe's history in their undisturbed state. The counterargument is equally compelling. Exploration is inherently disruptive. Every step forward, whether sailing uncharted oceans or landing on the moon, has required trade-offs. If we prioritize silence over all else, we risk stagnating, cutting ourselves off from resources, knowledge, and even potential contact with other civilizations. Some might argue that cosmic silence is a luxury we can't afford, especially when the survival of our species could depend on expanding beyond Earth. Perhaps the solution lies in balance. Just as we've established marine sanctuaries and quiet zones in national parks, we could designate regions of space as acoustic preserves, areas where artificial vibrations are minimized or banned outright. Missions could be routed to avoid sensitive zones, and communication protocols might limit transmissions in certain frequencies. The Outer Space Treaty already prohibits harmful contamination of celestial bodies. Expanding it to include noise pollution wouldn't be a stretch. This isn't just about rules, it's about mindset. Recognizing cosmic silence as a finite resource shifts how we approach exploration. Instead of conquering the quiet, we might learn from it. After all, the universe's most profound revelations often come from listening, not shouting. As we venture deeper into the cosmos, the choice isn't just whether we can make noise, it's whether we should. The quietest places in the universe aren't just empty, they're portals to understanding existence itself. Think about what silence means here on Earth, the pause between heartbeats, the stillness before a storm. Now scale that up to cosmic proportions, where the absence of sound reveals the universe's deepest workings. Black holes don't just swallow noise, they stretch the very concept of sound until it unravels. Cosmic voids aren't merely blank spaces, they're pressure gauges measuring dark energies push against gravity's pull. Even the quantum static of empty space, that faint hiss of particles flickering in and out of being, tells us that true silence might be impossible, and that impossibility teaches us more than any explosion ever could. Consider how much we've learned by listening to nothing. Gravitational wave detectors like LIGO don't hear collisions between black holes directly. They sense the quiet between the ripples, the way space-time itself rings like a muted bell. The cosmic microwave background isn't just leftover heat from the Big Bang. It's a fossilized whisper of the universe's first vibrations, now cooled to near silence over 13 billion years. Every breakthrough in astrophysics seems to come from the same realization. What we thought was emptiness is actually a rich tapestry woven from the threads of silence. This isn't just about physics, it's about perspective. In a world saturated with noise, the universe reminds us that clarity often comes from subtraction, not addition. The silent zones of space are like cosmic meditation chambers, forcing us to confront questions we'd otherwise drown out. Why does the quantum vacuum refuse to be quiet? What does the hush between galaxies say about dark matter's grip? The answers aren't just academic, they reshape how we see reality. When scientists cool atoms to near absolute zero to study their quantum states, they're not just chasing cold, they're chasing quiet, because only in stillness can the faintest signals be heard. Perhaps the most humbling lesson is that human noise is a temporary anomaly. Our radio broadcasts have barely traveled 100 light years. Our spacecraft are just whispers in the solar wind. Against the cosmic timeline, our species' entire existence registers as less than a blip, a reminder that the universe's default setting is quiet, and we're the brief interruption. That's not pessimism, it's inspiration. It means every discovery we make in these silent realms is a triumph of curiosity over scale, a testament to our ability to listen where others might only hear nothing. So the next time you gaze at the night sky, remember, you're not just looking at stars, you're looking at the universe's grandest quiet, a silence so vast it contains everything from the birth of galaxies to the last sigh of heat death. And somewhere in that stillness, the next great revelation is waiting not as a shout, but as the softest of whispers. If you've enjoyed this journey through the cosmos's silent places, hit subscribe for more explorations where science meets wonder. The universe isn't just speaking, it's been speaking all along. We're finally learning how to listen.